always takes about 30 seconds to set everything up. Okay, all right. We are all set up and ready to roll. So thank you everybody for joining us this week for Schedule B of the Monsoon Seminar Series. There's been a little bit of a time change for some of us, but for some of you, it's at the same time. So thank you again for attending and bearing with us as essentially we've updated the schedule for this time of year. And so before we get started, just housekeeping rules as usual. I mean, most of us are veterans for the seminar series. So please just remember to type your question into the chat so that we can all see the question, and then I will call on you to read out your question, or I can read it out for you. And then I think that pretty much covers it. So without further ado, I would like to welcome Dr. Xiaoli Zhou from Hongji University joining us today to tell us a little bit about continental weathering and ocean chemistry. So please.
Yeah, thank you for your introduction, Tara. So I'm very happy to have the opportunity to present some of my work here. So I guess this is not very, this is quite different from what the other speakers who talked about more about monsoons on the shorter time period. So today my talk will be focusing on the multi-million year time scale during the Cenozoic. So I'll discuss the continental weathering from the point of view of ocean chemistry. Okay, so why do I care the ocean chemistry? Because this is important because it will affect minerals, proxies, and the carbon cycle. So the figure shows here is the major ions in the chemistry that changes dynamically over the whole Cenozoic. So the ocean chemistry, for example, the ratio of magnesium to calcium ratios, it affects the mineralogy of marine orthogenic calcium carbonate. So when the magnesium to calcium ratio is high, the calcium carbonate mostly exists as aragonite. And when the ratio is low, it is mostly calcite. So other than that, ocean chemistry also affects many trace metal proxies based on foraminifera, such as magnesium calcium ratio, strontium calcium ratio, etc. And lastly, but also very important, ocean chemistry also affect the carbon system, which include the carbonate saturation state or the omega, and also which is tightly coupled to the atmospheric PCO2. So this is for the whole Cenozoic, Phanerozoic, but this talk will only focus on the Cenozoic. By the way, for the rest of the talk, I will show the time from left to right, so from the past to present. So this figure shows that over the Cenozoic, both the temperature and PCO2 have been decreasing. Based on the oxygen isotope of benthic foraminifera and proxies of boron isotope and alkanones. But why there is a long-term cooling over the Cenozoic? This question is still not fully resolved. And because the temperature is partly controlled by the PCO2, many people have tried to answer this question from the point of view of PCO2. So there seems to be a PCO2 puzzle or paradox because on the multi-million time scale, the PCO2 in the atmosphere is relatively balanced between its sources and sinks. So the major source of CO2 is from the mantle degassing. So the CO2 in the atmosphere will dissolve in the water and reacts with silicated and carbonate rocks on the continent. And this will deliver bicarbonate along with some cations such as calcium and magnesium to the ocean. And these ions will turn into calcium carbonate and precipitate on the seafloor. So on the long term, the sources of CO2 from the mantle degassing and its sink as calcium carbonate are relatively balanced. So that means if the source have been constant, then the sink should also be relatively constant. And based on the work of Rowley 2002, his work showed that over the last 180 million years, the seafloor spreading rate has been relatively constant, which is shown here by this black curve. So this means that the sink of CO2 as calcium carbonate should also have been constant, and CO2 should not have varied a lot. But this is different from what we observed from the previous slide, that CO2 has been decreasing. So how come when the source of CO2 was relatively constant, but the concentration of it in the atmosphere was decreasing? So there have been two major hypotheses to explain why this is as is. One of it is the uplift hypothesis, which was raised by Maureen Ramo, William Rodman, and John Kuspa in the late 80s and 90s. So basically, their hypothesis assumes that the uplift of Himalayas have accelerated the continental weathering, which consumed a lot of CO2, and it resulted in the decrease of CO2 in the atmosphere. So these hypotheses have been supported by 3 lines of evidence. The key evidence comes from the strontium isotope, which is the upper right figure. So the continuous increasing trend of strontium isotope has been explained by the increased weathering from the uplift of Himalayas. And the second line of evidence comes from the carbon isotope, which was explained as more weathering of organic carbon, which released more carbon-12 enriched carbon into the ocean. And the third line of evidence comes from the changes of the CCD, the carbonate composition depths. So this was explained by the increased weathering or the input of alkalinity to the ocean. However, there's a big problem here because there is not a negative feedback. That means if the weathering of CO2 continuously reduce the CO2 concentration, within a very short time period, the CO2 would be completely consumed. But we have not seen such a runaway condition over the Cenozoic. And so the second hypothesis was the black or the geocarp model. So this hypothesis, there is a negative feedback loop there, and it also takes into account of the weathering of different rock types at different times. So in this model, basically the CO2 is balanced between its source from the volcanisms and its sink as calcium carbonate. And during this process, the other ions such as magnesium and calcium were also coupled to the change of carbon. And that, so perhaps we can learn something from the ocean chemistry, especially magnesium and calcium. So over the next half an hour, I will mainly talk about how the calcium has changed over the Cenozoic and what it means for the carbonate system and CO2 in the atmosphere. And at last, I will try to find out what has caused the changes in calcium. Okay, so first, how did calcium change? There have been several other proxies that have estimated calcium in the Cenozoic. For example, the most widely cited record is from fluid inclusion. However, there are several drawbacks. First, the distribution of fluid inclusions is very sporadic. So we only find 3 data points here over the whole Cenozoic. This is marked by the gray diamonds. And second, it is most of the fluid inclusion samples were found in the coastal area or in separated basins. So whether they can represent the open ocean or not, it's still a question. And thirdly, the age constraint is not very accurate. So there's an uncertainty of about 2 million years associated with the age determination. Lastly, but also very important, calcium was already depleted in the fluid inclusions when people try to estimate calcium from these inclusions. So the estimate of calcium from these inclusions were based on the assumption of the product of calcium and sulfate. And so other than fluid inclusions, there were also other records based on calcium isotopes. For example, the green and blue records are based on biogenic calcium carbonate, and the purple is based on the calcium isotope of autogenic barite. And these records show very dynamic changes in calcium over the Cenozoic. Other than these proxies, there are also models. For example, here, this dashed line shows the model result from Woolman 2001. So all these records all show different trends. So we need a new proxy to find out how did calcium exactly change in the past. So here I will introduce a new proxy based on the sodium-calcium ratio in foraminifera. And why the rationale is as follows. Because the residence time of sodium is very long. It's at least larger than 65 or 50 million years. And that for calcium is only about 1 million years. So the sodium concentration probably has not changed a lot during the Cenozoic. And this is also supported by the model result in Tyrrell and Zivi's 2019 paper. And so if the sodium-calcium ratio in 4M is proportional to the ratio in the seawater, then there's a potential that we can use sodium-calcium ratio in 4Ms to estimate the calcium concentration. And this proxy has several advantages over the other proxies, especially the fluid inclusions. And first, it can provide a continuous high-resolution record. And second, because it is tied to accurate stratigraphy, so it can has accurate age control. And thirdly, it can be testified by culture experiments and core top samples. So this proxy has been testified by 2 sets of experiments based on benthic 4M of operculina and also 3 species of planktic 4M. So the left figure shows you the experiment result from on the benthic 4M, which shows the sodium-calcium ratio in the shells, in the 4M shells, increases with the sodium-calcium ratio in the solution. And also the right figure shows you the result on the planktic 4Ms. So both of these 2 sets of experiments show this, the increase of sodium-calcium in 4Ms with the ratio in the solution. And so if the sodium concentration is constant, then that means the sodium calcium ratio in the foram will increase with the decrease of calcium. So these two sets of experiments used different equations to describe the relationship between the ratio in the shells and that in the solution. And we tend to use the linear regression here, and I will talk about that later also. So that's the culture experiment result, but we also want to know whether the sodium calcium is also affected by other variables. So here is the core top data for 3 benthic foraminifera, the Euvidrina species, the Woolostorphi, and Ambonatus. So these circles, squares, and diamonds represent each of these species. And blue and orange represent samples from the Atlantic and Pacific Oceans, respectively. So we show that the data show that the sodium calcium varies among each species, but generally we don't observe a strong change with other variables such as temperature, salinity, or carbonate saturation state. We do found a slightly increasing trend with carbonate saturation or the delta carbonate, but whether that holds true for the downcore samples, we would like to test that. So for that, we measured a core in the North Atlantic Ocean, which is shown on the right figure. So we measured sodium calcium in 2 benthic species over the last 160 kilo years. So the black curve shows the oxygen isotope, which shows this covers a whole glacial interglacial cycle. And the two sets of blue dots are the sodium calcium. So although over this glacial interglacial cycle, the temperature, salinity, and also carbonate saturation state probably have varied a lot, we don't see any significant change in the sodium calcium. So now we're confident to apply this proxy to downcore samples that have larger ages. So here is a map showing where our samples come from. So most of them come from the Pacific, equatorial Pacific Ocean, and also in the Atlantic. There is one from the Indian Ocean. And we analyzed the sodium calcium in 3 species of foram, 1 planktic and 2 benthic foram. So here's the result over the last 43 million years. The top panel shows the sodium calcium in the planktic foram secutifer. And the middle one is for Woolostorphi. So both of these 2 records show the sodium calcium have been increasing from 15 million years ago toward present. And for Ambonatus, we generated a longer record. It extends back to 43 million years ago. So this record shows the sodium calcium was relatively constant from 43 to maybe 10 million years ago. And most of the change happens in the late Neogene, probably over the last 5 million years. But we still see a similar trend in the Ambonatus to the other 2 records. And before we apply this proxy to the downcore records, we have to find out the distribution function of sodium calcium. And this is the data I showed you before for the culture experiments for secutifer. So the green dots are directly from the culture experiments. We can't directly apply this equation to the downcore because we observed an offset between our core top values and the culture values. So we shifted the calibration vertically to get the calibration that can be applied to the downcore samples. So here we use the red equation. And because we observe a similar average value of sodium calcium in Willisdorfi versus secutifer, so we adopted the same equation for Willisdorfi. For Ambonatus, we adopted the same slope but a different intercept. And here, by using those equations, we reconstructed the calcium concentration in seawater over the last 43 million years, which is shown here on the upper right. So overall, the calcium concentration have been decreasing from 43 million years ago toward present. And most of the change happens in the last 15 million years. Compared to the oxygen isotope record and the PCO2, so here for the calcium record, I used a lowest. I performed a lowest on the raw data, so you can't see the detailed change here, but you can probably can still see some correlation between the calcium with the oxygen isotope. For example, in the Eocene Oligocene transition, or in the MI3. Okay, so how does our record compare to the other ones? So this shows that our record is generally consistent with the fluid inclusion records within the uncertainties. But our record provides a much higher resolution record compared to the fluid inclusions. Okay, now we know how the calcium has changed over the Cenozoic, but what does it mean for the carbonate system? The carbonate saturation state and the carbonate ion concentration are important for the carbon cycle and also marine organisms. So the carbonate saturation state, or the omega, is determined by the product of calcium concentration and the carbonate concentration, and divided by the solubility product constant, or the KSP. So based on this equation, we are able to calculate the carbonate ion concentration. As long as we know how the omega, KSP, and calcium have changed. Although the KSP also depends on temperature, but that effect is quite small. So we tend to assume the KSP has been relatively constant. So now, if we know how the omega has changed, then we'll be able to calculate the carbonate ion concentration. So how has the omega changed? The CCD, or the carbonate composition depth, has been used as a proxy for omega. So the figure shows you how the CCD has varied over the last 16 million years. So these are from Palicki 2012 and also from Campbell 2018. The second record has considered the changes in topography. So both records have shown that the CCD has been relatively constant or slightly deepening in the past 16 million years. This means that the omega has also been constant or slightly increasing toward present. So how does our record compare with these two? Before I showed you how we can get the calcium concentration from sodium calcium, and we also have records of boron calcium ratio, and it can tell us how the delta carbonate ion has changed. So combining these two records, we can generate the record for omega, which is marked here as the red curves. So generally, our record is consistent with the other studies. It is relatively constant or slightly increasing over the last 16 million years. So here omega is plotted upside down. So higher values is toward the bottom, and it corresponds to deeper CCD. And we also compared the carbonate ion concentration in the bottom water from the boron calcium with the modeled surface water carbonate ion concentration marked here as the green and blue lines. So they are also relatively constant, relatively consistent. Okay. So what can these records tell us about the CO2 concentration in the atmosphere? Because the PCO2 is related to the pH and the carbonate ion concentration. When we have higher carbonate ion concentration, the pH would be higher. So these the hydrogen concentration would be lower. And because there's a square here, so PCO2 is more influenced by the pH. And so, for example, in the early Cenozoic, when we have high calcium concentration, if everything else is the same, then we should have lower carbonate ion concentration and lower pH. So and higher pH and higher carbonate hydrogen concentration, hydrogen ion concentrations. So this will give us a higher PCO2 concentration. Well, at present, when we have lower calcium concentration, we have higher carbonate ion concentration and lower PCO2. And this is also confirmed by the modeled result by Zibi and Tabriel 2019 here. So more toward present, we have higher carbonate ion and lower PCO2. Okay. So now we have now we know how the calcium has changed and what are the implications to the carbonate system and atmosphere CO2. So what has caused the changes in calcium? To answer that question, we should start from the calcium cycle. The major source for calcium in the ocean is from continental weathering, and the major sink is the precipitation of calcium carbonate. There's a minor source from the hydrothermal vent, and there's a tiny part of calcium is removed as evaporite, but here we will not consider it because it's too small compared to the others. So in order to change calcium concentration, we have to change either the continental weathering or the hydrothermal flux or both of them. So because there's no easy way to assess which parameter changed, we will look at the sink of calcium first, which is the mass accumulation rate of calcium carbonate. So these are some photo cores of ODP sites. This is ODP 982 from the North Atlantic. So just by looking at the colors of the cores, we observe whiter color toward the bottom and darker on the top. So the top, from top to the bottom is from Pleistocene to the mid-Miocene. So we observe a whiter color in the mid-Miocene. And a similar feature has also been observed in the South Atlantic at ODP 1088. So also whiter colors toward mid-Miocene. And also in the Indian Ocean at ODP 758. So why there's a whiter color in the past and a darker sediment toward present? Is that because there was more calcium carbonate precipitation in the Miocene and a decreasing mass accumulation rate toward present? So inspired by these observations, my colleague Wei Ming, who is now a postdoc at Brown University, did this work during his PhD. So he requested samples from over 30 cores from Pacific and Atlantic and Indian Oceans. These cores all come from areas where the calcium carbonate percentage are high. So the red color represents higher calcium carbonate percentage. And these cores forms 3 transects. So this is where the samples are located in 13 million years ago. So basically they form a transect in the Western Pacific, in the equatorial Pacific, and also in the Atlantic. So so basically he estimated the mass accumulation rate, the MAR, of coccoliths and foram from all these cores. So these 5 figures shows you the MAR from the shallowest site at each location. So for each figure, we observe that the MAR in the mid-Miocene was much higher than in the Pleistocene. So although we can see some variations there, but the general trend still holds. And most of the change is driven by the coccoliths rather than foram. But I will not dig into that detail here. So those records are all from the shallowest site. So why do I show you the shallowest site record? This is because the carbonate will dissolve partly as the depth gets deeper. So for example, here we take the 4 sites on the Ontonjava Plateau in the Western Pacific. So for each color bar here, they show the records from 1 depth. The 3 bars here from left to right represent the MAR of carbonate from Pleistocene, mid-Miocene, and late Miocene and mid-Miocene. So we can see a higher MAR from the mid-Miocene and lower in the Pleistocene. And we also observe a sign of dissolution along the depths. So the MAR gets lower and lower with deeper at the deeper sites. And also we observe the stronger dissolution in the Miocene. For example, when we compare the record from 806 and 804, we see half of, or we see that the MAR at 804 is almost 1/3 of that at 806. But in the Pleistocene, it's only halved. And I'll show you in the next slide why and how strong this dissolution is. And we similarly in the Eastern Equatorial Pacific, we observe a similar trend. Okay, so how do we assess the dissolution? Traditionally, we use the fraction of sediment that is larger than 33 microns over the bulk sediment. However, there's a problem here because the rationale behind this proxy is that we use the fragmentation of foram to indicate how strong the dissolution is. However, there's a lot of foram coccoliths here, as I show you before, and also here. So most of the sediments is coccoliths. So we have to remove the coccoliths before we use the proxy. So Weiming developed or improved this proxy by removing coccoliths. So it's called coccolith-free size index. So he calculated the larger than 63 micron over the larger than 20 micrometer fractions. And this can also be observed under the SEM photos. So this is for the coccoliths, and this is mostly coccolith-free fragments. So when we apply these proxy to the past, here I will show you the data from four sites on the Ontonjava Plateau. So the left figure shows you the calcium carbonate percentage. It shows that these data have been slightly decreasing from maybe the late Miocene toward present. So does that mean the dissolution has been stronger toward present? So his data show that it's the opposite. So higher size index means less dissolution or better preservation of the carbonate. So from 15 million years ago toward present, the size index has been increasing. So that means the carbonate has been preserved better and better toward present. And this can also be confirmed with the photos. For example, these two sets of photos shows you how the sample look like from 803 and 804 from different depths. So in the mid-Miocene, we can see more fragments at both sides. But in the Pleistocene, we see many complete foramen shells. Okay, so let's put them together. So I have shown you how the preservation or the burial of carbonate has been changing over the last 16 million years, and also how the dissolution has been changing. So because what we preserved on the seafloor, it comes from what deposited from the top, and also minus what has been dissolved. So far we observe a higher MAR in the mid-Miocene, and also more or stronger dissolution in the Miocene. So if we put these two together, the deposition of calcium carbonate or the production of calcium carbonate must have been higher in the mid-Miocene and lower toward the Pleistocene. That means the higher production in the Miocene outcompeted the stronger dissolution at that time. And so to summarize it, the decrease in MAR from the mid-Miocene toward present, it is not due to dissolution, and it is also is either due to the increased weathering based on the Ramos hypothesis. Rather, it suggested a decreasing weathering input of alkalinity to the ocean. So other than weathering, what other variables may have contributed to the changes in calcium? So this is a very recent paper. It is just published. This paper shows you how the production rate of ocean crust has changed over the last 18 million years. So this red curve shows you the blue shades shows you the new record. So generally, it shows from the mid-Miocene toward present, the seafloor spreading rate and also the production rate of crust has been decreasing. So generally, we think that the hydrothermal flux is proportional to the seafloor spreading rate. So that means the hydrothermal flux of calcium has also been decreasing from the mid-Miocene toward present. Okay. So other than calcium, the changes in weathering and hydrothermal can also affect other elements like lithium and magnesium. So here I show you a record of the downcore record of lithium-calcium ratio in the foramen on the left. And on the right, I combined this lithium-calcium record with our new calcium record. So this shows you in the last 15 million years, the lithium concentration in the seawater has been decreasing. So this can also be explained by the decreasing weathering flux and the decreasing hydrothermal flux. And how about the magnesium and alkalinity? As I showed you at the beginning of this talk, the magnesium, calcium, and bicarbonate are coupled. So they are delivered to the ocean from the river, and they are removed as calcium carbonate and also some dolomite. And over the hydrothermal vents, the calcium is released to the ocean, but magnesium is removed from the ocean. So how does the weathering and hydrothermal flux affect the magnesium? It should have increased the magnesium. And this is using the magnesium record from the fluid inclusion and combined with our new calcium record, we computed the magnesium calcium ratio in seawater, which is marked here as the red curve. So generally it is consistent with other records from calcium carbonate veins, large benthic foram and corals, and also many models. What about alkalinity? How does alkalinity change? So based on the model of Xavier and Tyrell 2019, they suggest that the alkalinity has been relatively constant throughout the Cenozoic. This actually in turn confirms that the changes in calcium must be accompanied by the changes in magnesium, so that the alkalinity associated with magnesium and calcium can be balanced. All right, so a short summary. So our data suggests that the sodium-calcium ratio in foram can be used as a proxy for seawater calcium ratio. And our records suggest the calcium concentration has been decreasing from the early Cenozoic toward present, and most changes happened in the last 5 to 10 million years. Our high-resolution calcium record can help us understand how the carbonate saturation state and PCO2 has been behaving over the last 40 million years. Fourthly, our records suggest that the changes in continental weathering on its own cannot drive the changes in calcium, and the decrease in hydrothermal flux must have played a role in reducing the calcium and increasing the magnesium and calcium ratio. Lastly, our record suggests the magnesium calcium ratio has been increasing from the early Cenozoic toward present. And also most of the change happens in the late Neogene. And that's all. I'll stop here and take any questions if there's any.
Great, thank you so much for your talk. That was a very well explained, I think, talk of a variety of different proxies, I think.
I hope so.
That at least I'm less familiar with some of those. So I'll give everybody a moment to put their questions into the chat.
Okay.
Yeah.
Xiaoli, I have a question.
Mm-hmm.
Hi. So, Tara, could I just ask a question now?
Yes, go ahead.
Okay, right. Thank you for the good talk. This is the second time I listened to this, and still something to think about. So what have you thought about this change you described in relation to the start of the monsoon, not the the monsoon variability between glacial and interglacial, but the start of the monsoon, maybe 15, 13 million years ago?
Yeah, actually, a PhD student in our group did some work on the Miocene, and his work found that the changes in the ocean chemistry is actually maybe related to the start of the Western Pacific warm pool. So that may be related to this, the start of monsoons. But I think there would be, there needs to be more evidence to, to link these two.
Mm. No, I was sort of thinking of Dick Krohn's work in Arabic Sea and something related to the tectonics of the Tibetan plateau. And people were talking about 7-8 million years ago, and now your record is much earlier. And obviously the monsoon or the Asian monsoon started 15 million years ago, if I remember correctly, or is still debated. And then just having all these linked together, do we see any change in seawater?
Actually, I think I didn't put my boron calcium record here, but it's very similar to the carbonate saturation. Oh, okay, here. So do you see the hump around 8 or 7 million years?
Right.
So our boron calcium ratio also suggests a similar trend. So there's a hump here in our boron calcium ratio. But we didn't see that in our sodium calcium ratio. So maybe it's reflected in the carbonate, the calcite saturation state or the carbonate ion, but maybe it's not the effect maybe not so big to affect calcium that has a higher residence time or larger residence time.
Okay, thank you.
Yep.
I don't necessarily have a question, but more of a comment. I think that this record will be useful for, I think, especially for those of us who are, I guess, wrapped up more in the continental weathering side of this story. Yeah, because that's mostly the realm of like CO2 and weathering feedback that I've been wrapped up in. And I know that there's still an incredible amount of debate about the role of continental weathering. I mean, even just, I think last week I saw that there was a big comment reply between a few studies about mafic weathering and the magnitude of that and how seawater isotopes may or may not reflect that. And I think one of the interesting things that you also mentioned in your talk is about how constant is this hydrothermal rate and essentially the sea spreading rate. And I liked that you brought up at the end of your talk this kind of reevaluation of that.
So this paper just came out a few days ago. If you are interested, I think you can.
Yeah, I made a mental note of that. Yeah, I mean, it's I feel like it's like if you blink in the community, there's a new paper, and of course, like, yeah, there's just, again, so much debate. But I think that at least from my point of view, your record looks quite resilient in terms of the calcium seawater curve. So
thank you. Yeah, I think these paper are using more accurate age controls and also some new methods that I'm not familiar with, but I feel their record is quite convincing to me. Yeah,
and I think a lot of these records, right, they span from pretty much the Miocene to present. And I think that a lot of us are really quite hungry for older records as well, because I mean,
so in this paper, the authors said they will be extending this record to older time intervals.
Nice.
So yeah, this is the first try, you know. So it's because the recent time intervals we have better preserved samples, so it's easier to do.
Yeah, we should watch the space. Yes.
Yes. Yeah. Agreed. I think all of us are hungry and eager for all of this. So does anybody else have any other questions?
I think the Brown group, they are continuing working on this topic. I think Wei Ming, my colleague Wei Ming is trying to model, like combine the weathering input and the hydrothermal input, and I hope he'll have some result soon.
Nice, nice. Do I dare ask if you are going to be extending your record, or what's next?
Yes, why not? Yeah, I have a few data points in the not Cretaceous, but close to it, but I haven't interpreted yet. But it seems like the sodium calcium in those records are much lower than in the Eocene and Miocene. So it seems like calcium have been continuously changing in the same direction toward like, older ages.
And I guess, I mean, of course, when you go back, there's just more variables you have to take into account. And as you said, I mean, once you get back past, what, 100 million years, you said, your sodium starts not being so constant. Well, so, yeah.
Yeah, and diagenesis, you know.
Yeah. Well, I guess if no one has any more questions, we'll let Xiaoli off the hook here. And so I would welcome everybody to put your hands together to thank Xiaoli for sharing the talk today. And so before you all run away, I just want to remind you that the next monsoon seminar will be happening on the 6th of April. I believe Yama Dixit will be giving us a talk about their research. And I think with that, that's it for today. So again, thank you, Xiaoli, for an excellent talk.
Thank you.
Everyone has, and hope everyone has a nice evening, afternoon, and morning. Okay, thank you.
Bye-bye.
Bye.